I think I've mentioned this before, that early predictions of changing sea level were not right. Also want to remind you that the application for the apprentice research program at UCSB is due at the end of this month. And I think that the sooner that you apply, the better. So if anybody was thinking about it, you actually get a stipend after having a spectacular research experience during the summer at UCSB. This is like the most serious science thing I can mention for people your age. This is it. Like next year, half of you are going to come asking you for an internship doing something environmental, and I'll be like, oh, do that thing that you should have done last year. I'd like to talk briefly about greenhouse gases, which is study goal number 20. I wrote some notes on the board, but they may be confusing. You'll need more notes on your paper. Then I want to talk about how the ocean is changing, and we have kind of a lot of study goals on that. And then I want to try to squeeze in El Nino maybe briefly, and then talk about predictions for the future. Hey, did we talk about climate models yesterday? Yeah. These slides you saw? Okay. So here's number 20. Please look up. I think you may have some of this in your notes already if you did your homework, in which case I would just be adding a few things. I hope you can all see the writing goes all the way down to the bottom of the whiteboard. For study goal number 20, I'd like to talk about the main greenhouse gases. The primary greenhouse gas is not really humans' fault. We're not changing levels. The majority of the greenhouse effect is made by plain old water. That's the main greenhouse gas. And it has not changed due to human activity very appreciably at all. There may be a little bit more water vapor as part of the positive feedback of climate change in the lower atmosphere, but it's a negligible percentage of total water vapor. The main greenhouse gas is water, and it's not changing very much. It's not really something that we affect. The next biggest greenhouse gas is CO2. And that's probably the biggest chunk of how we change temperature. That's a big part of our climate change, of the amount of climate change that we are doing is the CO2. We've raised the amount of the atmosphere by about 55%. So remember, those numbers are the change in CO2. That's gone up about 55% due to human activity. Most of that comes from fossil fuels. A little bit from forest fires, like setting fires, like deforestation in the tropics sometimes. But almost all that comes from fossil fuels. And I hate to say this, but like everything you like about your life is probably powered by fossil fuels. Like imagine if you won the lottery and you really wanted to indulge, that would probably have a big carbon impact. Like, this is my life. I'm not trying to make fun of you. Like, if I won the lottery, I'd probably buy a badass car, cause more climate change. Maybe I would take a flight to Hawaii, cause a whole bunch of climate change. Maybe I get a bigger boat and use more fossil fuels while I'm at it. If you see like a really poor person who has to like lift their water out of a hole in the ground and walk it back home and try to farm their food on some crusty sand in the middle of the desert, that life that you don't want is probably not a part of this problem. Like, basically our quality of life is leveraged on our fossil fuel consumption. As a global rule, I hate to say this because it's me too, I'm not making fun of you, like I saved up for many, many years so that I could finally splurge and get myself a boat, and that's where I put most of my gasoline. For spring break, I'm going to take my boat and burn a bunch of gasoline after I tow it all the way to Mexico. Like all the things that we value, or almost all of them, the indulgences in our life are almost all of them powered by fossil fuels, and that's kind of proportional to our CO2. So all the cool stuff that we buy, all of our doohickeys and whatchamacallums, all of our cool electronics, like that electricity is made with fossil fuels. Like right now, our life is really made to leverage fossil fuels into our indulgences and thus create a bunch of CO2. That's a big bummer. Another source of greenhouse gases that humans make is methane, that's CH4. Fun fact, methane per molecule is way hotter than CO2. It has about 10 times the heat storage of CO2. So it gets like 10 times hotter and then gives off 10 times more heat than CO2. Isabel, put your phone away. That's 10 times more heat than CO2. It's 10 times worse than CO2 in heat terms. Again, we've raised those levels really significantly in the atmosphere. And this comes from agriculture. You read right, that says cow farts. So apparently, like, herbivores in the wild don't really fart a lot, but we don't like to eat wild herbivores. We say that they taste too lean and meat and like gamey. We like to eat fatty herbivores, and so we have to give them like weird indigestion to make them fat, so they taste better. And so fattening cows makes them fart a lot, and when they fart, they have a whole bunch of carbon that they haven't been able to break down. So anyway, cows fart a bunch of methane. That's real. Like, it's a huge amount of our methane. Like, I wouldn't mention this if it was just a punchline. Like, I like talking about farts, but that's enough now. Like, that's a whole lot of methane. Like, there's actually a project trying to figure out how to put, like, a little tiny burner behind cows to light farts. I'm not kidding, and make that methane into CO2.
But would then the sponge be moved onto the CO2? Like
CO2 is 1/10 the greenhouse potential. So any place that we can light methane on fire, we should. Yeah.
They can burn farts while they're in it, so it's like good either way.
So there are methane capture methods in most slaughterhouses now and indoor feedlots and stuff. We're like trying to figure out how to capture all that methane. It's like actually a real thing. Like, it's a lot of friggin' methane. It's a lot of global warming from cow farts. Overall, agriculture makes a lot of methane, and the production of fossil fuels also makes a lot of methane. Nitrous oxide comes from agriculture, especially fertilizers. And that's not changing very much. That's a small amount of our greenhouse gas changes. And then I have to point out that there's a whole category of greenhouse gases that are man-made and entirely new to the atmosphere, which are very hot. These are molecules that wobble really hard, so they can store a lot of heat. The hottest greenhouse gases are the industrial greenhouse gases. Stuff like CFCs. SF6 is 20,000 times hotter than CO2. So we don't really make a lot of these gases, but they do a lot of heating when they get there. Does that make sense? Like really, really high heat volume, even though there's not a lot of the gas? It stores a ton of heat in just a few molecules. And those are entirely man-made. They were never in the atmosphere before. So the majority of the greenhouse effect we're not really changing, that's just water vapor. The majority of our change comes from CO2. The next biggest chunk of our change comes from methane. There's a few greenhouse gases that we change in small amounts. And there's a category of really hot gases that are new to the atmosphere. We just added them. Those are called the industrial gases. Would anybody like to ask me about the things I just said or put on the board? Yeah.
So the 0% in the H2O isn't 0% in the atmosphere, it's 0% climate change?
0% our change. So humans are not affecting
Okay.
the amount of water in the atmosphere directly. Yeah.
When you say like those industrial gases are like all new, like how long ago did they become like relevant in our
Some of them probably just in the last 15 or 20 years. Most of them started becoming noticeable in the 80s. Some of them go back to the 50s. Pretty much after World War II, we got into a new level of chemistry. So you could, almost any big chemical change that affects the president is World War II or younger. Greenhouse gases anymore from anybody? No more greenhouse gases? Let's talk about the ocean. We got to skip around. Please go to study goal number 21. Yeah, that's the next one. 21. There are two key parts of number 21 that I'd like you to add to your notes. I think one of them might have been in your homework, the other one probably is not. First thing I want you to put in your notes, water stores heat really well. So when you heat up the planet, you're really just heating up the ocean. Almost all climate change is just ocean heat change. If the planet went up by 1 degree, that would be the temperature of the ocean going up by 0.95 and the temperature of land going up by 0.05. Water has a higher specific heat capacity. So global heating is basically just ocean heating. That's where most of the heat goes. Of course, this affects evaporation, like where there's water vapor.
What did that make so there's more vapor in the atmosphere?
It does.
But it doesn't change, like you need to say when it comes to
Well, A, we're not doing that directly, that's indirect, so we don't make the water vapor, we make the water hotter and it makes more water vapor.
Yeah.
So like it's technically considered indirect water vapor gain. Separately, there's still roughly the same amount of water vapor in the atmosphere at any one time. Like the amount that it's growing is knowable, but it's not crazy gigantic. It's not a big change in the total volume. The other thing I want you to add in that study goal, maybe you'll remember from the ocean, the mine drainage thing in the last, when we talked about water pollution. What happens when you mix oxides with water?
Acid.
You make acids, and so keep in mind, the ocean has a whole lot of water, and because we're making more CO2, there's more carbonic acid in the ocean. This is not a climate thing, but it doesn't really fit our class anywhere else. So in study goal number 21, I'd like you to add just that one detail, that water plus CO2 makes carbonic acid.
What's the chemical formula for carbonic acid?
I think it's H2CO3.
You're standing right in front of me.
H2CO3.
Okay, thank you.
And adding more carbonic acid to the ocean is shockingly significant. Temperatures always change, pH rarely changes. If I could hack your body and raise your blood temperature by 1 degree, you'd be totally fine. And if I could hack your body and lower your blood temperature by 1 degree, you really wouldn't even notice. 1 degree temperature change in your blood is kind of irrelevant. But if I could hack your body and change your pH by 0.01, you'd be dead. Like, pretty instantly. I don't know how much chemistry you all have, and I don't have a ton of time for this either, so I just want to make sure that we're all clear about something. All chemistry depends on pH. So changing the ocean's pH turns out to be way more devastating ecologically than changing the ocean's temperature. In the global scientific community, this was a bit of a surprise. In the 80s and 90s, there was all these coral bleaching events, and everybody thought that it was from pollution, and then everybody thought it was from ozone, and then everybody thought it was from temperature. And really, it took like another 20 years for people to notice the pH changes. Ocean acidification is a crazy way that the ocean is changing because of this CO2 that we're adding. And it's been way more powerful than we thought it was going to be. It's had huge changes to ocean ecosystems from the pH change. Okay. I want to try to show you something complicated. Aoife, go microwave this until it's pretty hot to the touch. Bronson, go bring me my tub of ice cubes from the refrigerator. The freezer, please. Okay. I'm going to try my best I'm going to try my best to show you something pretty dynamic and kind of complicated and hopefully memorable.
Why would a human die if it changes pH by small?
Because basically all the pH in your all the chemistry in your body happens differently at different pH. So you ever seen like the deodorant says pH balanced for a man or whatever? pH balanced for a woman? I'm gonna take that in just a second.
So you got cockroaches under your posters.
Oh really?
Yeah.
Well, if you want to see a happy chicken, go feed them to the chickens.
Oh, he ran away.
You heard me say feed the chickens.
It's not a matter of scary, it's a matter of something
Okay. Please be quiet. I'm going to try my best to show you something interesting. Is that really hot?
No.
I want it to be like almost hot to just like
It's like warm.
hotter. I'm putting blue on one side.
Is it blue or is that stuff that dries us?
It's blue.
No, I mean, like,
Wait, was that you?
Like the methylene blue.
yeah, like is it blue like blue food coloring or like the
You know what it is? It's shut up, Sadie. Got her. I don't know, dude. It's blue food dye, I guess. I don't know.
That was the question.
I still don't know. I'm sorry. It just says blue dye. I don't know what kind of dye it is. It's blue though.
I wasn't asking what kind, just because we use methylene blue, which is something.
Okay.
Okay.
That's cool. Leaving stroke with that.
A, my model leaks. B, it'll be interesting for about 5 minutes and then it'll also be purple.
Yay.
C, I gotta do a little bit of lecture and then come back to this and then get back to my lecture. So this is not a timeout even though I'll be distracted for a moment. By adding water to the ice, I've made an ice bath. The temperature of this side is going to change quickly now that it's immersed in cold stuff. And I'm also going to make this side a little bit hotter. And in the next few minutes, something interesting is going to start to happen. Merely by changing the temperature of the two extremes, I'm going to create something interesting in this water. And then it's going to be purple, which is not it. I'll show you why this is important. It's laid out in that particular spot for a very carefully planned reason. First, please look up. There's this thing in the ocean called the ocean conveyor belt current. Study goal number 25. The ocean conveyor belt current is a tremendous body of water. And it moves really, really fast by water volume terms. Something like 2 billion gallons drop off the surface of the ocean per second or something. Like the net down force is the biggest current, it's the most water, it's the biggest energy transfer on our planet. This is the world's largest heat exchanger. This current is a very interesting way of moving water through the planet. If you can please look up at my map on the screen, you can see that there's hot water moving along the surface in one direction and cold water moving along the bottom in another direction. The kids who are sitting up in the front might be able to see what's happening by making water hot and making water cold. What's happening?
The blue in the bottom.
What's happening?
You change the pressure in both sides, so the hot water and cold water are moving to different pressures.
Does anybody notice that this looks suspiciously like something else of the exact same? Right? So there's probably some water vapor coming out here. Heat exchange to the environment at the top. High pressure where all the hot water is rising, so it expands sideways. High pressure where all the cold water is sinking, so it expands sideways. By making some water hot and some water cold, I make it move laterally. Know about that? Now, please look up here. By making water hot in one place and making water cold in another, I might be able to make that water move sideways. The heat source here was the microwave IFA hot water. And the cold source here was the freezer ice cubes Bronson. Notice that everything cool in our society is powered by fossil fuels, by the way, microwaves and freezers. Yeah.
Wrong.
Why is it moving in like that specific way? Why not the other way?
I got you, fam. It's moving in that specific way because of the contours of the bottom of the ocean and where heat comes from, where cold comes from. So in your notes, heat comes from the Indian Ocean is a bunch of hot water trapped at the equator. Look at this. You can keep writing in a minute. Look over here. That's a whole bunch of hot water at the equator. So you get this equatorial pool of hot water. And then the cold comes from a whole bunch of wind across the Atlantic. Like blowing across the top of steaming soup. You all realize that cools off your soup when you blow all the steam away? Everybody got that?
So it comes from the north and south poles?
Nope. It does not.
Oh, those steam at the bottom.
Hey look! It's going to be purple in a minute because all the blue is sneaking into the red side and eventually it just gets all swirled together. So it's about to happen. This is the last moment. You can see I made water move sideways just by changing temperatures. If those tubes were from here to Alaska, I could still make water move sideways. Because hydraulic pressure is consistent across all continuous water. I could go to the moon. And if there was a temperature differential at the ends, that water would move sideways. So I can move water all the way around the planet by having a source of heat, the Indian surface, and a source of cold, the Atlantic wind. Yeah?
If the temperatures were more extreme, would the water move faster?
Yes?
Right, and also, I'm like, this is kind of related to the warm-up, but I still don't get how it like relates to it.
I got you, fam. Now, this is related to the warm-up because when you move the water around, you're going to change conditions. By which I mean, please look over here. I'm delivering hot water to an area that was otherwise cold. Right? So what I'm actually doing is I'm heating the cold area and I'm also chilling the hot area. Right? That's a heat exchanger. So up here, wherever that hot water ends up, they just got a heater. You all see that? Wherever the cold water ends up, they just got a cooler. We have this really weird phenomenon on our planet. These details are mostly not on the AP test. I'll let you know the parts that are relevant. But I want everybody to just look up at my map for a minute. From the Indian Ocean, just follow the arrows. Where does the hot water go to? The North Atlantic, right? I'd like you to consider something interesting. Anybody help me find England? Is that England?
Yes.
Yeah.
That's England?
Yes.
Doesn't matter.
It actually does. It actually, for this, this one time, that's why I don't know where it is, because I never otherwise care. All right.
I mean, you're pointing at Ireland.
Okay, look. The United Kingdom. The United Kingdom.
Yes.
This is a fascinating punchline. I swear, this is like next level climate science. I'm serious. This will help you at a party. Watch. And you need help, trust me. That's the United Kingdom. Everybody except Bronson. That's the United Kingdom, right there. And the United Kingdom has something really special and weird. Look at that exact latitude if you were to go across the Atlantic. I don't know if you're aware, but that's basically solid ice 24/7. This entire latitude, the Aleutian chain, northern British Columbia, what is that called? No. Queen Maudlin?
Canada.
Yeah, whatever. Northern Canada. Northern Canada. Northern Canada. Like, if you go across that band, these are some really cold parts of the world. Is Mongolia over here somewhere?
Yeah, kind of, sorta.
Mongolia's lower. Okay, great. So we're in a really cold part of the planet. Except if we go across that latitude, we also have the United Kingdom, where it's like grass everywhere. How come they don't have grass? How come they have grass everywhere and they don't have no grass?
Because of the thing.
Because of the thing, the what? Say.
The wind blows the hot stuff onto them.
Yeah, the wind blows the hot stuff onto them.
Which makes the ocean.
This is actually a crazy, profound observation that right now, because we have hot areas and cold areas, what we are actually doing now is we're moving heat around. Like this. To answer your question, we are moving, naturally, our planet moves heat in weird ways. So all the heat from the Indian Ocean is being carried to England so they can grow grass when they should be permafrost. The United Kingdom, if you just look at latitudes, should be frozen ground. And of course the United Kingdom is not frozen ground because they're getting heat donated, they're getting heat delivered. By the way, all that hot water is leaving, so they're getting air conditioning. And all of this hot water is leaving because it's being drawn around by this current. The one part that might be on the AP test that you should know is that the ocean conveyor belt is a huge heat exchanger. It moves heat around. Takes away heat from the Indian Ocean, adds the heat to Europe. And climate change is about to turn it off. Climate change is about to turn it off. This is also relevant to the AP test, I think. The ocean conveyor belt current is slowing down fast.
Because all the water's getting warmer?
It is slightly because all the water's getting warmer. It's mostly because fresh water floats on salt water. And we're adding a whole bunch of fresh water where it used to sink. Because Greenland is melting. So melting Greenland makes the Atlantic fresher so it doesn't sink anymore. And so we've basically stopped this movement. So now all the steam is staying over here. They're getting bigger monsoons. And that means the heat is not delivered to Europe. So punchline, I'm sorry to drag this out so far, I know it's complicated. When the planet gets hotter, Europe will get colder. Because we're going to stop delivering India's heat to Europe. Which is why Russia had a big drought. Which is why they stopped exporting food to Syria and northern Africa. Which is why there was massive destabilization because they were restricting food supplies in parts of the world that relied on food aid from Russia. Which is why a bunch of climate dorks say that climate change caused the destabilization of Syria and Sudan. That's such a complicated answer. I would never expect you guys to be able to say that on a test. That's not going to be on my unit exam.
The whole thing? Or just the last part?
But the parts that you do need to know is that this is a giant heat exchanger, and climate change has stopped the heat exchanger. So some places will get colder when the planet gets hotter. You do have to know that. Yes?
How did this affect Russia? Like,
Okay, I got you, fam, but then I'm going to move on. Look, if you blow across the steamy soup, that's going to put a lot of water vapor into the European jet stream. And when you stop bringing the hot soup, then you're not putting water vapor into their jet stream. So Russia's food production has declined tremendously because they have less rainfall. Basically, for the last 20 years, Russia's had below average rains almost every year.
So it's basically like the same thing with Europe, just like really stretched out.
Yep, and P.S. London has had some of the coldest winters. Strangely enough, people who live in the United Kingdom would tell you that they have like unseasonably cold winters because they don't get that delivery of hot water anymore.
Chill in America.
Let's see.
Put a jumper on.
So let me see if I can get one last study goal in. I want to do number 29, and what you wrote down from the book was fine, but I want to add other stuff. If you could make a note, I'd like to come back for 23 and 24 another day. And right now I want to talk about number 29. Your book had a list of how climate change affects rivers, sea level, biodiversity, coral, agriculture, and human health. I want to add to that list. You can all imagine I've been watching climate predictions ever since I was your age, and I've kind of collected some of the ones that I think are the most like basic and not weird guesses. These are like just the straightforward realities of climate change, not really crazy predictions. I think I have 11. So I can give you 11 interesting predictions about climate change for study goal number 29. Number 1, weather patterns are changing all over the world. We've already seen this. Unusual weather is becoming more common everywhere because we've destabilized the system. A good way to think about this is if we shuffled all the basketball players into weird new teams, games would be really weird. If we just rearrange the NBA into a whole bunch of new teams, every single game would be like, what the hell is going on right now? That's climate. We've rearranged all the variables so every little iteration is new and unique. All weather is destabilizing. This is a global trend everywhere on the planet. All humans are getting weird weather. Like for us, we had weird droughts, and then we've had weird fire seasons. All over the world this is happening. Number 2. This sucks for biodiversity. And there's a term I want to remind you of. That term is ecosystem shear. Climate change won't kill a single species because of the heat. Nobody dies when you make the planet 1 degree hotter because the planet's 1 degree hotter. The reason that ecosystems suffer is because the relationships in the food web start to fall apart. That's what ecosystem shear means. That the pollinator's not there when the flower opens. That means that the seeds aren't there when the migratory bird shows up. All those relationships between species, all the arrows I drew on the board like 6 months ago that you drew them all on paper and then we did all the other layers on the board, you remember that? Those are the ones that fall apart. Species don't die because of the degree of temperature difference, they die because their food is gone. Or they die because their symbiosis is gone. Problem number 3. We've already seen that global agriculture will go downhill. If you're a farmer that's used to growing potatoes, it takes a while to switch out of the potato thing. When we change weather patterns, agriculture goes downhill. And this has already happened. We've seen this. Global food production is down. It's been down for a few years now. agriculture zones suffer. Number 4, the global water supply is changing. As glaciers melt, water supply is running out. For you and me, that's not a problem, but roughly 1/3 of humanity drinks the Himalaya. That's an important variable that you and I don't really have to think about. Please look up. The 2 most populous nations get the majority of their water from the Himalaya. So as those glaciers shrink, the amount of water in those rivers goes down. That has impacts on the water supply of China and India. That's about 1/3 of our species. Number 5. I told you about this before. Now it comes back, and you all know I'm right because the proof is in the pudding. New diseases. We get hungrier, we get thirstier, we move around more, and that just makes us sicker. Overall, disease becomes a bigger problem for our species. You could say that's ecosystem shear. Our relationship with microbes is shifting. We're more susceptible to some microbes, we're exposed to some microbes more. We are moving microbes in new ways. That's basically just ecosystem shear between us and the things that make us sick. The World Health Organization believes that the most dangerous thing about climate change will be the changes in diseases. This is probably the one that keeps me up at night. Number 6, we know that sea level rises, and remember, that's because water is bigger when it's hot. It's called thermal expansion. 1/3 of humans live within 300 feet of sea level. So sea level rise really matters. It's not like anybody's going to drown, but imagine the cost to your economy when sea level goes up. I want you all to imagine something. How many feet are we from sea level?
20.
Do you mean from like here or like above sea level?
You all see what I did there? If you didn't see what I did, let me try this again. Look at this, look at this. We're like, I don't know, a couple thousand feet from the beach, but we're 17 feet up from sea level. 1/3 of humans live within 300 feet of sea level. That's a long way back on the coast. That's a lot of humanity. And here's why that matters. No one's going to drown from sea level rise. It's not like all of a sudden, like, oh my God, here goes the ocean. And you're like, it's not like that. No one's going to drown. You won't even get your feet wet unless you want to. But if sea level rises 16 feet, imagine what's between me and the ocean. Wait.
Build a wall.
Maybe we'll get good at this wall building racket. Remember that if sea level rises 16 feet, what's between me and the ocean? Like the wastewater treatment facility is 1.5 feet above sea level. That's an expensive thing to rebuild. The train station is 2 feet above sea level. The airport is 3 feet above sea level. Yeah, the 101 is only a few feet above sea level in a bunch of places. Imagine having to move all that. The homeless shelter, having to move the zoo, you know, all the waterfront. Like, here's what I'm getting at, and I got to move on really quick. When we talk about sea level rise, everybody imagines this like tidal wave, and that's the wrong problem. Like, no one's gonna drown, but the strain on your economy. Do you all realize that almost every capital on the planet is on the coastline? Like Sao Paulo and Buenos Aires and Santiago and like, hey, you know, cool thing about Sacramento, our state capital, is it's at sea level anyway. It's just on the river delta instead of being on the coast. Los Angeles, San Francisco, San Diego, Seattle, Portland, Washington D.C., our national capital, is right above sea level. Everybody mapped our world via boat. So all the cities are on the coastline. So when sea level rises, that's just a drain on our economy. Moving all those train tracks and all those harbors and all that wastewater treatment. Imagine what that means for our economy. We say sea level rise and everybody's like, oh, the ocean! And like, no, just worry about the money.
But Jose, like most of the really rich people in our country live on the ocean, so they would be like, it's just give them some money and then we can move.
There's probably going to be winners and losers, and like the fact that my waterfront property isn't waterfront yet. Maybe I'll just hold out and I'll be fine. But like, you've seen what happens to our global economy when some people, you know, worry about illness. You've seen what happens to our global economy when Saudi Arabia cranks up petroleum production. What do you think happens to our economy when most major cities on Earth have to invest huge amounts of money in rebuilding their infrastructure? Imagine what it would cost to Santa Barbara to move all that stuff. Like, what's down there? Like, just the economic burden of that. Like, it's taken us 50 billion years to add a lane to the 101 and we're not even halfway done? Great. Great. And then I'm thinking about, like, just rerouting the whole 101 and the train tracks and the wastewater and the pier in the next 100 years? The City College, UCS Brodog, the airport, the harbor, we got 100 years, let's go.
We literally haven't even finished the pit.
That's just Santa Barbara.
I know, and that's my point about sea level, it's the money of just like trying to move all this stuff around. Number 7. Number 7.
What would happen if we like didn't move anything around at sea level and if that
It lands.
We're going to find out really soon. Number 7. The ocean is acidifying. This has huge impacts on fisheries. All the chemistry of the ocean is different. We can't grow oysters anymore, y'all.
No.
I hope you've eaten your oysters. If you don't like oysters, you should develop a like for oysters. Because your kids ain't going to have no oysters. Number 8. You know, when we change currents, we change international relationships. Like, can you imagine if it was too expensive to make our stuff in China, but now it got cheaper to make our stuff in Chile? Like, what would that do to the global economy? Number 9. Number 9. The severity of hurricanes goes up. Not the number of hurricanes, but the severity of hurricanes. Let me explain really quickly. Maybe you can understand this. The severity of a hurricane depends on the difference in temperature between the ocean and the air. If they're the same temperature, you don't get a hurricane. If the ocean is way hotter than the air, you get a big hurricane. And all global warming is ocean warming, so we are increasing the difference in temperature between ocean and air. So number 9, we're making the severity of hurricanes worse. Number 10, I'm almost done, but I got to finish before the bell. Number 10, what's going to happen to our global economy when food is hard to get, people have changes in water, diseases everywhere, we're dealing with new international relationships, and we're rebuilding all of our coastal zones? I wonder if our economy is going to benefit from that. It's interesting to consider that somebody's going to make money, but it's probably going to be something new. Our economy is going to change in ways the economy hasn't changed yet. And number 11, environmental